In this video, we're going to do the next example in our handout for stoichiometry and the ideal gas law. So what mass of sodium azide is required to produce 65 liters of nitrogen gas that is required to safely inflate an airbag? Assume that the reaction occurs at 32 degrees Celsius and 108 kilopascals. Remember that nitrogen gas is N2. Here's the equation provided to us, and so I'm just going to rewrite it because that would be our first step. If it wasn't given to us, we'd have to write a balanced equation. And so we have sodium azide, 2 moles of it, 2Na N3 solid. That's a solid sodium azide. It's going to decompose and it's going to produce some nitrogen gas, which is what inflates the airbag, plus 2Na solid. And so let's write out the information that we have. So we know that we want to produce 65 liters of nitrogen gas. So our volume is going to be 65 liters. And what we want to figure out is, well, what mass of NaN3 needs to decompose to do that. And so to find the mass, remember that we have to do mass is equal to moles times molar mass. And so really, what do we need here? Well, we have the molar mass of NaN3. That's from the periodic table. So let's write that out. So we have 3 times 14.01 plus 22.99. And that gives us 65.02 grams per mole. So all that's missing now is the number of moles. That's what we need to find. Now we're given that we want to produce 65 liters of N2. And so what we can do is we can find the number of moles of N2 under these conditions and use a mole ratio to find the number of moles of NaN3 and then convert that to mass after. So let's write out what we have for this. So we have volume over here. We also have the pressure, which is 108 kPa. We have the temperature, which is our 273.15 plus 32 degrees Celsius, because it has to be in Kelvin. So that's 305.15 Kelvin. We also have the R value, which is 8.314. That would be kPa, liters, mole, Kelvin. And we can find the moles of N2 using the ideal gas law, because remember that we have PV is equal to nRT, and this is a gas over here, so we can use that to convert to moles. And so we know that the number of moles is going to be NPV over RT, and that's how you find the number of moles. So let's go ahead and do that. So step one is basically write everything out that we know about the substances in our equation. Step two, let's find the number of moles of N2. So the number of moles that we do know is equal to the pressure. So 108 kilopascals times the volume, which is 65 liters. And we're going to divide that by the RT. So we have 8.314 kilopascals liter over mole Kelvin times the temperature, which is 305.15 Kelvin. We can cross Kelvins out, we can cross liters out, we can cross kPa out, and we're left with moles at the end. So let's go ahead and do that. We have 105 times 65 divided by 8.314 divided by 305.15. And so we get approximately 2.76702944 moles of N2. And so now what we're going to do is we're going to use our mole ratio to figure out the moles of NaN3. So our mole ratio is that we have 3 nitrogens for every 2 sodium azides. And so that's going to be that the moles of sodium azide is going to be equal to 2.7670290044 moles of N2. Now, you don't have to write all those digits down, but do keep them in your calculator just to make sure that you're not rounding too early, times 2 moles of NaN3 for every 3 moles of N2. And so the N2s cancel out. So we have basically just times 2 divided by 3, and we get 1.84468629 moles of NaN3. And so now what we're going to do is we're going to find the mass. Our mass is going to be equal to the number of moles times the molar mass. So N times molar mass, which is equal to that 1.8446, keeps going, moles times 65.02 grams per mole. Cross moles out, and we're left with grams, so times 65.02. We get 119.941486 grams. But don't forget, we have to write a therefore statement and round to the proper number of sig figs. And it looks like the smallest number of sig figs is going to be 2. So we can write our therefore statement. Therefore, the mass of sodium azide required is approximately, we said 2 sig figs, I believe. So we can round up over here to 120 grams. So 120 grams of sodium azide would be required to decompose to make 65 liters of nitrogen. If you want to double check that you're on the right track, you could always just work backwards. So we have 120 grams of sodium azide. We can divide that by 65.02 to get the number of moles. We can then look at our mole ratio and do times 3 divided by 2, and we get 2.76 moles of N2. And then we can go ahead and figure out the volume from the PV is equal to nRT. So it would basically just be your moles times your 8.314 times your temperature, which was 305.15, divided by your pressure, which was 108, and you would get 65 again. So I just did it backwards to double check my work, and it looks like I was on the right track. And so in the next video, we're going to take a look at example number 5. But in this one, we simply did a mole ratio. We had to convert this to moles first using the PV is equal to nRT. As we see from our flow chart over here, if you have a pressure, temperature, volume, and you need to convert to moles, use PV is equal to nRT. It's manipulation to get number of moles first. And then afterwards, find the number of moles and then convert to whatever you need. So if you want to convert to mass once you have the number of moles, you simply do times the molar mass.